Okay. A quick review, some stuff that we did in relation to one of these signed problems for this time. Okay. If we have 100% annual interest compounded n times annually, then your principal function, as you can easily figure out, your rate is 100%, which is 1, right? So every period, if you're compounding n times annually, you divide that rate by n, you get 1 over n. And you add that to what you have, just like we did before. And then in t years, you'll do that n times every year, so that in t years you'll do it nt times. That's the meaning of this expression. Okay? Now we want to look at the expression, and the p naught is your initial value, okay, your initial principal. Then 1 plus 1 over 1 plus 1 over n raised to the nt, this expression here, can be expressed as 1 plus 1 over n to the n raised to the t, just by the fact that when you raise a power to a power, you multiply the powers. So what we want to do is we want to look at just this 1 plus 1 over n to the n expression and how it varies as n gets larger and larger. Because as we've seen, the more times you compound your interest, the more money you get. But after a while, it really doesn't make much difference. If you compound it enough times, it doesn't matter how many times you compound it, you're not going to get that much extra. Now, that should come out of some of the problems that were assigned. We'll see how that worked out. So, what we do then is we let n get bigger and bigger and see what this factor is, because that's what we're going to multiply by this for every year. Okay? So we do this. Let n be 1, then 2, then 10, 100, 1,000, etc. Now we carried etc. to the point where n became 1 billion, at which point somebody's calculator crashed, so we stopped there, but some people got a little further than that. Okay, well, if n is 1, then 1 plus 1 over n to the n is 1 plus 1 over 1 to the 1. 1 plus 1 over 1 to the 1. And it doesn't take much to see that 1 plus 1 over 1 is 2. So it's 2 to the 1. And no surprise, that's 2. Okay? So if you compound at 100% once a year, you double your money, because that means you're adding 100%. Now, if you compound twice, then this 1 plus 1 over n to the n becomes 1 plus 1 half to the second power. And we evaluate that at 3 halves to the second power, which is 9/4 or 2.25. Now, the rest of these are going to come out in decimals, and you would need a calculator to evaluate them. You really don't want to be raising 11/10 to the 10th power by half. Okay? You could do it. Whether you could do it without making a mistake, I don't know. I don't think I could. Okay. Yeah, if I was careful enough and did enough double checks, I could. Okay. So if n is 10, this becomes 1 plus 1 over 10 to the 10th, 1 plus 1 over 10 to the 10th, and that's 11/10 to the 10th, and that's 1.1 raised to the 10th. Because, you know, a lot of ways to think about that, and if you wanted to see all the details, you can look at the MCR videos. That's 2.59. Now, when you go up to 100, you get the similar expression that you probably can't read because it's written pretty small. It comes out about 2.70. You go to n equals 1,000, you get about 2.7169 something, so it rounds off to 2.717. Now notice I use 3 significant figures here, or 3 decimal places instead of 2, because it's getting pretty clear that this is going to be changing in the future by less than one number in this decimal place, if you just look at the pattern. Well, if you go all the way to 1 billion, 10 to the 9th power, you get this, which is equal to this, 2.718281827. Okay? And then you kind of think, if you've done all the numbers in between, that this 2.7 is probably going to become a 2.8. So you get 2.71828, 1828. Okay? And at that point, you'd be excused if you decided, oh man, that's just going to keep repeating 1828 forever. Okay? If your calculator doesn't take any further than that and you don't know any differently, that wouldn't be a bad conjecture. But it turns out not to be so. Okay? So, you know, we had one calculator that took it out to an extra significant figure and got a 5 here. So clearly this pattern gets broken. Okay? And as it turns out, any pattern at all will eventually get broken. If you let n be bigger and bigger and bigger, this thing has to go out to more and more significant figures before you can see the change between two calculations. And then we had somebody that actually got to take it out 5 more figures past this. We got a 45904, which doesn't look anything like a 1828. Turns out this is a number that keeps going forever without ever repeating itself. I mean, without ever, okay, there's no sequence of numbers that keeps repeating forever. There's no pattern that keeps repeating forever. Okay? So this is a non-repeating, non-terminating number. Then we can say, well, you know, these numbers are getting pretty big, right? Well, of course, there's no end. You could keep doing this. If you had a calculator that would calculate it, you'd keep doing it till the end of the universe, if you live that long, which you won't. No offense.
Depending on when the universe ends, though.
Huh?
Depending on when the universe ends.
Don't expect the universe to end in your lifetime. Okay?
Oh no, we got asteroids coming for Earth and all kinds of stuff.
Yeah, I know, you know. I mean, you know, everybody probably has the idea at some point in their life that the universe just ended. Okay? Dang, it's ended the universe. Nah, probably worse than that. Okay. Yeah, the universe is still here, and you still have to suffer. That's life.
So true, though.
You get over it. Okay. Okay, so we say now that, well, we consider the limit of this as n approaches infinity. Now when I say you can keep doing this forever, okay, or you can set a supercomputer, just keep doing it forever, and make sure that computer knows how to replicate itself so that when it dies, it can pass its information on to its replica, okay? Or maybe it makes a bunch of replicas. Anyhow, you just keep calculating this thing. It never ends. So we say that in that case, n would be getting really big. It would be approaching infinity. Okay, it never gets there. You can't ever get to infinity, so this thing has to just keep going and going. And that's kind of an imaginary thing because nothing can. But in the limit as n approaches infinity, this number approaches something that starts out like this, but gets a lot longer. Okay? Before it stops changing. And the number that you get we call E, which is maybe the most important number in mathematics. It's foundational. From E, for example, you get pi.
Oh, man.
Now, you don't want to know how.
Nope.
I mean, I could easily tell you. Calculus students, first-year calculus students are learning right now. Okay? So they're about to know. Or at least they're about to have the machinery to understand it. It's not that hard if you know a little calculus, but you don't. So I'm not going to explain how you get pi out of E. I'm just saying you can. You do. Okay, well, now let's look at what this has to do with compounding your interest, because n is the number of times you're compounding in a year. So as n approaches infinity, well, what happens to the length of time that you spend compounding? Okay, well, it's going to approach 0. We'll see why. Well, if n is 2, that means you compound your interest twice a year. If you understand compound interest from the stuff we've done, you understand exactly what that means. If n is 12, you're compounding monthly. Well, twice a year, that's a period of 6 months before you compound again. Monthly, compounding every month. 6 times as many times. That's 6 times as short a period. Weekly, you'd be compounding 52 times in a year. And of course, a week is shorter than a month. Daily, well, days are shorter than a week, and the n would have to be bigger, right? Every second, what would n be? Well, just figure out the number of seconds in a year. 60 times 24 times 365 and a quarter. Okay? Like 30 million. Okay? So that would be every second. Well, as that approaches infinity, the time gets shorter and shorter, and you start getting to the point where you compound continuously. Okay? As n approaches infinity, you approach continuous interest. And we got to have a way to calculate that so your bank can advertise continuous compounding and get you to invest. Continuous compounding. Continuous compounding and daily compounding don't differ by much at all. But if you say continuous, okay, that can get that can make it interesting. It's easy to calculate continuous interest. Okay? And if it's continuous, well, what does this become? As n approaches infinity, this approaches e, right? So this expression approaches e to the t. So your principal function, which is p naught times, p naught times this, basically, becomes p naught times e to the t, where p naught is your initial investment. The investment you have at t equals 0 times e to the t. Okay? So that's where e comes in. Then, and I'm not going to go through the details. As I said, if anybody emails me asking for a short video on the details of how we get this, you may. But it involves a change of variable, a little more sophisticated than I expect most pre-calculus students to understand, although some of you might well. I'm sure some of you would. But in a pre-calculus class, I don't expect more than 25% of students to be in a position to understand that, so I don't talk about it. Okay? If you want the supplement on that, let me know and I'll do it. Okay, interest rate R compounded continuously gives you this principal function. And it's closely related to this function. It's just that with this function, R was 100%, which is 1. If R is 4%, then R is 0.04, and you'd have e to the 0.04t, okay? So, we have this problem that I'll write out a little bigger on the next board, and we're going to solve it. Figure out at continuous interest, 4%, invest $1,000, when you're going to have $10,000. How much you're going to have after 2 years, 5 years, 10 years, okay?